Somewhere beneath the coast of Northern California, something has been moving in the dark for millions of years and nobody knew it was there. Not the geologists who mapped the state's faults for over a century. Not the engineers who built its bridges and its cities on top of what they believed was solid, well-understood ground. A hidden slab of rock, broken away from an ancient tectonic plate, has been quietly sliding beneath the Earth's surface, and scientists have only just found the evidence hiding in thousands of earthquakes, too small for anyone to ever feel. What they uncovered does not just rewrite a science textbook. It changes how experts think about the earthquake risk facing millions of people living along one of the most dangerous stretches of coastline on the planet. For decades, the story of California's earthquake risk seemed mostly settled. Everyone learned the same simplified version. 3 tectonic plates meet off the coast near Humboldt County at a place called the Mendocino Triple Junction. South of that point, the Pacific Plate grinds past the North American Plate, and that boundary is the San Andreas Fault, the most famous fault line in the country. North of the junction, another plate called the Gorda Plate dives underneath North America in a process called subduction, and that zone is known as Cascadia, capable of producing some of the largest earthquakes on Earth. Clean, simple, 3 moving pieces on a map. That was the picture for generations of scientists, and it shaped how officials planned for the next major earthquake in the region. But a team of researchers from the United States Geological Survey, the University of California, Davis, and the University of Colorado Boulder just proved that picture was incomplete in a way nobody expected. Their study was published in the journal Science in January of this year, and it did not come from a single dramatic earthquake or a lucky discovery at the surface. It came from something almost invisible, a method built on patience and thousands of tiny tremors buried deep underground. These are called low-frequency earthquakes, and they are nothing like the shaking most people picture when they hear the word earthquake. They are thousands of times weaker than anything a person could ever feel standing on the surface. They happen quietly, deep below, in places where one slab of rock slides slowly against another. For most of scientific history, these tiny signals were treated as background noise, barely worth a second look. But researchers realized that if you track enough of them over a long enough period, they begin to trace the outline of something hidden. Something like an iceberg, where only a small piece shows above the waterline and the true shape is buried below. Lead author David Shelley from the USGS Geologic Hazards Center described the challenge in exactly that way. You can see a bit of the structure at the surface, but you have to figure out what the real configuration looks like underneath. So his team built a dense network of seismic instruments across the Pacific Northwest, sensitive enough to catch these faint underground signals, and then they did something clever to test their model. They looked at how these tiny earthquakes responded to the pull of the sun and the moon. Just like ocean tides rise and fall with the gravity of those two bodies, that same gravitational pull places a subtle repeating stress on tectonic plates deep underground. When that stress lines up with the natural direction the plates already want to move, the number of tiny earthquakes increases. It is a small, precise signal, but it acts almost like a fingerprint, revealing the true shape and orientation of the rock structures far below the surface where nobody can see them directly. And what that fingerprint revealed was startling. Instead of 3 simple moving pieces, the region actually involves 5, and 2 of them had been completely hidden until now. At the southern edge of the Cascadia subduction zone, the team discovered that a chunk of the North American plate itself has broken away and is being dragged downward together with the Gorda plate as it sinks into the mantle. That alone was a significant finding. But south of the Triple Junction, they found something even stranger. The Pacific Plate, as it moves north, is dragging a separate mass of rock underneath the North American plate. Scientists are calling it the Pioneer Fragment. This slab is a leftover piece of the Farallon Plate, an enormous tectonic plate that used to run along almost the entire California coastline millions of years ago, and has mostly vanished beneath the continent over time. The fault separating this hidden Pioneer Fragment from the rest of North America lies almost flat, and it cannot be seen or mapped from the surface at all. It has been sliding there silently the entire time. This discovery solves a mystery that had puzzled seismologists for more than 3 decades. Back in 1992, a powerful magnitude 7.2 earthquake struck the region at a depth that was far shallower than anyone expected based on the old 3-plate model. Scientists could not fully explain why. Now they can. Co-author Catherine Materna explained that it had always been assumed that fault lines simply follow the leading edge of a subducting slab. But this newly discovered example breaks that rule completely. In her words, the plate boundary is simply not where scientists thought it was. Think about what that really means. For decades, hazard maps, building codes, and public safety planning in one of the most seismically active regions in North America were built on a model that left out 2 entire moving pieces of the puzzle. That is not a small correction. That is the foundation shifting under the feet of the very science meant to protect people from the ground, shifting under their feet. And this discovery is not happening in isolation. At almost the exact same time, a completely different research team, this one led by Dr. Liliane Burkhardt at the University of Bern in Switzerland, uncovered something equally alarming happening much further south, along the fault most people already fear the most, the San Andreas. Her team built a model simulating an entire 1,000 years of earthquake history across Southern California, using data reconstructed from carbon-dated soil layers, tree rings, and written historical records. What they found is that stress on the southern San Andreas fault and its neighbor, the San Jacinto fault, has climbed to the highest level recorded in that entire 1,000-year window. In some sections, the strain has already pushed past anything the model had ever recorded. Here is why that matters so much. Northeast of Los Angeles, these two massive faults come close to touching each other at a narrow mountain corridor called Cajon Pass. Geologists have a specific term for a locatio point that essentially decides whether a rupture stays contained on one fault, or jumps across and tears through the next one as well. History shows this gate can behave in completely different ways depending on conditions. In 1857, the massive Fort Tejon earthquake ripped through more than 200 miles of the southern San Andreas fault, but it stopped right at Cajon Pass, sparing the San Jacinto fault entirely. But in 1812, evidence suggests the opposite happened. A single earthquake appears to have torn through both faults at once, doubling the destructive power of the rupture. According to Burkhardt's model, right now, both faults are under near-record tension, and critically, that tension is nearly balanced between them. That matched stress pattern is exactly the condition researchers believe swings the gate open, allowing a rupture to jump from one fault to the other instead of stopping. If that happens, the resulting earthquake would be dramatically larger and more destructive than anything confined to a single fault line. The consequences of a dual fault rupture through Cajon Pass would be staggering. This corridor is not just a geological choke point, it is also a critical transportation and infrastructure lifeline. Major highways, rail lines, and power connections all thread directly through that narrow pass. A major rupture there would not only devastate the densely populated Los Angeles basin and the inland valleys nearby, putting tens of millions of people directly in the shaking zone, it could also sever the very routes needed to evacuate people or bring in emergency supplies afterward. Dr. Burkhardt has been careful to stress that her research is not a prediction of exactly when an earthquake will strike. Nobody can offer that kind of certainty, no matter how advanced the modeling becomes. What her study does provide is a much sharper physics-based picture of just how primed these faults are right now, compared to any point in the past 1,000 years. It is worth pausing on just how difficult this kind of discovery actually is to make. Nobody drilled a hole thousands of feet down and pulled up a sample confirming the pioneer fragment exists. Nobody photographed it. Instead, a team of scientists spent years collecting an enormous catalog of earthquakes so small that not a single seismograph alarm would ever go off because of one. They then had to prove, mathematically, that the pattern those tiny tremors formed could only be explained by a previously unknown slab of rock sliding beneath the coast. That is the kind of quiet, unglamorous science that rarely makes headlines, right up until the moment it forces experts to redraw the map of one of the most dangerous regions in North America. It also raises an uncomfortable question that seismologists are now sitting with. If a structure this significant, an entire broken off, tectonic fragment large enough to influence a magnitude 7.2 earthquake, could remain completely hidden until now, what else might still be sitting undetected beneath other fault systems around the world? Northern California is one of the most heavily monitored seismic regions on the planet, packed with sensitive instruments precisely because of how dangerous it is. If something this large could stay hidden there for this long, similar surprises could easily be waiting beneath less monitored regions elsewhere. Put these two discoveries together and a much bigger picture starts to emerge. In the north, scientists just found two entirely hidden tectonic structures, reshaping what we thought we knew about one of the most complex and dangerous junctions in North America. In the south, researchers just confirmed that the state's most feared fault system, along with its closest neighbor, is holding more built-up stress than at any point in the last 10 centuries, primed in a pattern that has, in the past, unleashed some of the region's worst combined earthquakes. Neither of these findings comes with a date attached. Nobody can tell you if this happens next year, next decade, or further into the future. But both of them tell you something just as important. The models experts have relied on for generations were missing pieces, big ones, hidden slabs beneath the north, and dangerously synchronized stress beneath the south, both quietly building toward a moment nobody can precisely schedule. If a video like this helps you understand what is really happening beneath your feet, take a second to like it and subscribe. because this channel breaks down exactly these kinds of stories, the ones connecting new science to the real risks shaping the world around us. California has always lived with the knowledge that a major earthquake is coming eventually. What is changing now is not that fear itself, but the depth of understanding behind it. Scientists are not just watching the surface anymore. They are listening to whispers thousands of times too faint to feel, tracking gravitational tugs from the moon, and rebuilding 1,000 years of history from soil and tree rings, just to understand what is really happening far beneath the ground people walk on every single day. And what they are finding is that the earth beneath California is far more complicated, far more interconnected, and far more restless than anyone fully realized. The question is no longer simply whether the big one will come. It is which pieces of a much larger, more hidden puzzle will move first, and how far the damage could spread once they do.